The relentless rise of CO2 in the atmosphere is strongly related to the generation of electricity. About a quarter of the greenhouse gas emissions come from the energy sector, where coal, oil and gas are still the major drivers of the world's energy system. Many people say that to solve the global warming problem, we need a game-changing breakthrough in the development of new technologies. Fortunately, with the exponential growth of technology, we're able to develop more complex systems that might hold the miracle solution to the world's energy problem. Wind energy is a growing industry. Increasingly, we see new wind farm projects being developed and built every year. However, the construction of these conventional wind turbines is reaching a convergence point where the cost related to a small increase in the power output is too large to be economically feasible. To put the scaling into perspective, approximately 8 times of the materials are required to double the size of a conventional wind turbine. We also know that the wind is stronger and more consistent at higher altitude. This is the reason why wind turbines tend to raise their center hub as high as possible, but it can only go higher up to a certain point due to the structural limits and difficulties in the installation process. In terms of money, the massive towers, blades, foundation, and center hubs represent half of the price of the wind turbines. Now, what if we could remove the non-generating parts from conventional wind turbines and put only the generating blades at higher altitudes? In the end, more than half of the energy output comes from the last section of the turbine's blade. This idea was first developed in detail by Miles Lloyd in the early 80s, when he presented the mathematical equation for the potential of a crosswind flying kite. In general terms, the power output of airborne wind energy, or AWEs, is proportional to the wind speed cube. Therefore, doubling the wind speed will increase the power output by a factor of 8. Airborne wind energy is still a young technology. Many different types of devices have been developed by research and startup companies. In overall, they can be classified into 2 types depending on the generation style. We have ground generation and flight generation. The difference is mainly where the energy is being generated. For ground system, the theory consists in using the aerodynamic lift force generated on the wing of the kite, which will create a tension on the tether, unwinding it from the ground base and finally driving a generator. For flight generation, or also called drag generation, the idea consists in taking advantage of the high apparent wind speed that the kite feels when it's flying perpendicular to the wind direction. The increased velocity on the kite will drive the onboard propellers that work as a small wind turbine, generating the electricity on the kite and sending it down to the ground through a conductive tether. The potential of AWEs comes from the fact that they can generate the same amount of energy of a conventional wind turbine with approximately 10% of the material cost, having arguably the lowest cost per electricity generated of all renewable energy technologies. In addition, what really makes AWE attractive is that as it goes higher in the atmosphere, not only the winds get stronger and more consistent, but they are also found all spread out across the globe. This means that the AWE have the potential to be installed almost anywhere in the planet. We just need to make them go high enough to reach this high-quality renewable resource. Every technology has its challenges, and airborne wind is not an exception. AWEs require a seamless interaction between the automated control, aerodynamics, power generation, and avionics. To safely put a commercial device in the sky, it needs to have the reliability and performance of a current aircraft. Combined with the autonomous control technology, it will allow the kite to fly and generate power without the need of any human operator. This can only be achieved with countless tests, simulations, and design optimizations. The startup companies like Makani are saying that the system must have at least 1 year of continuous operational flight time to begin to prove their performance and reliability. Scaling the system also introduces a major constraint in the weight and drag from the tether, reducing the power output and making the whole design more challenging. Finally, there's still no established policies or regulations set in place for these devices. Social and environmental concerns have been raised about the kites being a danger to birds and potentially to humans in case of a failure. That is why AWEs are targeting to provide energy and prove the concept in remote locations such as off-the-grid communities, mining, or offshore sites. The road ahead for airborne wind energy is not a smooth ride. However, the benefits are too good to be ignored. AWE is the next generation of wind energy and will soon have a great impact in the world's energy generation. After it becomes mature, it will have the realistic chance of replacing coal, gas, and nuclear power. The potential of being able to be installed almost anywhere in the world, increase the capacity factor, and reduce the intermittency compared to conventional wind. This technology can eventually become the cheapest source of energy and is one of the reasons why people are calling airborne wind energy the magic solution to the energy problem.